Yeah, can you hear me?
Yes, sir.
Okay. So did you work on that problem? I think we did some 5 to 6 iterations. And did you work on the problem?
Yes, sir.
So what did you get?
So the value of f of xns is uh, minus 0.99, sir. Always. That is,
Okay. Okay, fine. So I'm using mic now, so I cannot hear you anymore. If you want to have anything, just text me on chat box. Uh, whatever I ask you now, just text me on chat box, okay? I cannot hear you now. I'm using mic, so I'm not using earphones. If you have anything, just text me. All right? Okay. Yeah, thank you. Thank you, Subramanyam. So I hope you understood things. See, yesterday, okay, let me share my screen. Uh, Yesterday, we are working with a function like x power 10 minus 1. So we plot that function, easy plot. So function is like x power 10 minus 1, all right? And I will go for grid on. Yeah. Here you go, here. It's getting stuck. Yeah, so this is the plot. This is the plot you have. Right? So you obtain some plot like this. I'm using desktop now. So you have, no, but I cannot trust it. This is your x. Your, so your f of x is this. Okay. And this is your curve. Your curve is something like this. All right. And here you go. This is like 1. So f of x is x power 10 minus 1. So this part of the curve we are not showing. So here also we have intersection, right? That means this is now minus 1 because f of minus 1 is also equal to 0. F of 1 is again 0. So we are interested somewhere here. So we took something like 0 to 1.3. So we have chosen the interval like this, so 0 to 1.3. So we are least bothered about this left side, all right? So we don't bother about this root. So this won't be bothered now. The same thing if you work with bisection method. the same problem. So I have the same question, f of x is x power 10 minus 1. And I have a is equal to 0. And b is what? B is, I think, 1.3, right? So b is equal to 1.3. So we need to use bisection method. If you have that tabular form, just compare that one with this bisection method. The root estimate we will find like this, a plus b over 2. All right. So now first one has no variable f of a times f of b less than 0. So root is in between a and b, and of course you will get this is less than 0. So now once you do this, you can find a plus b. So 0 plus 1.3 by 2. So how much you get? So you get 0.65. So we can take down the equations. So I'll say this is my equation. This is my, say, A. This is B. So this is like B here. So this is XNS and approximate percentage relative error or estimated percentage relative error is this. So all right. So equation number 1, A is equal to 0, B is 1.3, so 0.65. I don't have any previous iterations value, so for the first iteration, the error is 100%. I'm very far from my true solution. My true solution is what here? My true solution is 1. So I'm too far from a true solution. I got 0.65 as of now. So I go for iteration number 2. So iteration number 2, what do we do? Let me shift this. So I'll use another color here. Let me use some other color. Which color? I'll write in red. Right now. Yeah. So I have a 0.65. Then what must be my second one? If so, I do this. If what here? Now which condition we need to check? If f of a multiplied by f of xns less than 0. Okay, f of a is equal to what? F of a is -1. So a is 0, -1. F of xns, what did you get? Anyone, could you just text me on chat box? What did you get for f of xns? Just text me on chat box. Okay, minus 0.9865. So we obtained minus 0.9865. So f of xns means this one. Somebody. So this is my xns value. So f of 0.65. Just put it in your equation, 0.65 over 10 minus 1. So what do we get here? Yes? Okay, sorry, you gave me the answer, right? Minus 0.9865. So the product is positive. So therefore the root is in between. The root is in between where and where? Between not A and XNS, between XNS and B. So for the new interval, now this guy XNS becomes A and he will become as it is, okay, B. So now without second thought, my A is XNS. So XNS is 0.65 and B is again 1.3. Now again find the estimate in the second iteration. So we are not juxtaposing anything as of now. Maybe 1 second. Okay. So now in the second iteration, when I is equal to 2, in the second iteration, so XNS is A plus B over 2. So 0.65 plus 1.3 over 2. This is what? 0.975. Agree? So you have 0.975 here. So error percentage is 33.3%. Did you just observe this? You should have observed this one. See, when you compare this table with the table obtained with false position method, in the second iteration, for the second iteration, epsilon A is equal to, what did you get there? Anyone? What did we get epsilon A for FPM in the second iteration? Yeah, 48.2%. But now here, you see there we obtain something like this, 48.2%, iteration 2, and we used their FPM technique, false position technique, linear interpolation technique, regular falsy method. Okay, but now here we obtained 33.3. So for this function, we could say that bisection method is going to converge to the answer faster when compared to this false position method. So that is evident from here. And sometimes, what happens for certain functions, what happens in the further iterations, again, epsilon A may increase. Yeah. And again, further iterations, epsilon A may decrease. So it may, the trajectory would be something like up and down like that. So, but for most of the functions, we will see trajectory will come down. Okay. And number 3, again, same story. Again, what do you do if f of A into f of XNS? Again, same f of A, f of XNS less than 0. So f of A, so this is f of 0.65. So f of XNS, so this is f of 0.975. So what do we get? So what did you get for f of XNS, f of 0.975? Okay, negative 0.223. So f of 0.65 is, so finally, what do we get? Is it less than 0 or greater than 0? The product, is this less than 0 or positive? Just help me out. Just confirm whether or not it is negative. Just do it. You plug in that and just tell me. I think you must get positive. So again, the new root, the new interval would be, yeah, positive, good. So the product is positive. So therefore there is no root between A and XNS. So there must be root in between XNS and B. Now you have to write. See, in programming, what do you do? Every iteration you have to check for the interval as well. So now you have to update the interval. Now A becomes 0.975. So my A is 0.975 and B remains fixed 1.3. It's like fast position method. From what we are approaching to the root from one end. Okay. And 0.975 plus 1.3 over 2 is what? Okay. 1.1375. Correct. Thank you. So 1.1375, and you see 14.3%. See, we are coming drastically down when compared to false position method. By the time we, by the time we are at iteration number 3 with false position method, I think we have error 30.9%, right? So we have error there 31% approximately. But see, it is just less than that. 14.3%. So this itself indicates that for some category of functions, bisection method outperforms false position method. Usually for most of the functions, false position method outperforms bisection method. Okay, outperforms means superior, like he's surpassing. Yeah, but for this category of functions, but bisection method is an utter flop method when function is just touching the horizontal axis. Otherwise, if function is tangential to x-axis, and at that juncture, bisection method suffers like anything. Not only bisection method, almost all bracketing methods they suffer. So we have to adapt open methods for such kind of problems. Even open methods are also not that fruitful for such kind of problems. So there we have some separate measures counter-attacking when we encounter such kind of problems in numerical methods. So we will investigate them in laboratory, won't we? Because it's easy to work in laboratory. We just perform some coding steps and we can do things out. So on again, again you do. So you must get iteration number 4 like this 1.1375. See now B is changing here. Agree. In case of false position method, one limit got fixed for all iterations. But in case of from iteration number 4, we don't take again this 1.3. So now you just take the average. So you must get 1.05625. And the error is even down 7.1%. Okay. Iteration number 5 you take, so you would get 0.975. So 1.05625. If you take its average, so you would get 1.015625. And this guy is 4% approximately. Okay. See, with false position method in the iteration number 5, for the same question we obtained something like this. You take false position method, regular false in method, linear interpolation method. Why the name false here? In false position method, why the name false? Huh? Why the name false? Let me ask someone random. 56, Lalita, just unmute yourself and give me the answer, please. 56, Lalita.
Yes, sir.
Yes. In false position method, what is false there? Yes. You have problem with your mic. So
Roots are not actual, sir.
yes.
Roots are not actual. Then
Could you text me the answer, please? I could not hear you. Yeah, position is false, of course. Why? Means what is the false there? Which position is false? Yeah, great. That's good. See, by the means of false positions, we are converging towards the true solution. See, because you're drawing like a secant line passing through 2 points to the curve, and that secant line is passing through x-axis, and that is a false position. But by means of it, you're really venturing towards actual solution. Okay, but the only problem is you are attacking to the answer from only one end, not from either ends. See, we can overcome this problem. See, whenever you find that one of the interval is, I mean, one of the limit is staying fixed. Now, at that interval, you find functional value, and then you divide that functional value with 2. Okay. Then again, you perform same operation like f of a times f of x is less than 0 or not. So that thing again, I will try to show you in MATLAB. Okay. So good. So see in the iteration number 5. In the iteration number 5, what did we get? XNS. XNS, you obtained something. Yes. 0.407, right? So we obtained 0.40788 with approximate percentage relative error around 17.1%. It's drastic because we are going to get, I mean, we must get x equal to 1 as the numerical solution. See, in the iteration number 5 itself, you are really close, 1.015 with error percentage 4. In case of FPM, you're too far. Yeah, by the way, you came out of the solution really. Okay. Yeah. Are we clear so far? So you can go for, I think, by the time you reach 7th iteration, you will get almost 1.00001. Okay, 1.0, I think you'll get 0001. And that's truly close to your true solution. Are we clear so far?
Yes, sir.
Oh, great. So, okay, fine, thank you. Okay, now it's time to say bye-bye to bracketing methods. Let's invite open methods, error analysis, all the kind of stuff we will do in MATLAB. Okay. So let's introduce open methods. Open methods are risky, no, but they are faster when compared to bracketing methods. But see, when you go to open methods, the clever or the judicial choice of what you call initial guesses will play a role. Okay. So we can use a technical word like judicial choice. Now, the meaning of judicial choice is that it should have true meaning of that function. You should be able to identify the behavior of the function. Then only you can make a proper choice. So judicial choice of initial guess is vital. Initial guess or guesses. Yeah. Initial guess or guesses is important. Is can use a word paramount. It's really important with open methods. Okay, so we will discuss, as on the course, you have fixed point iteration method. Fixed point iteration method. This is quite a headache method. It should have proper, selective functions. It should know functional behavior for this. And second one, we will study like Newton's method. This is probably the famous open methods. One of the famous open methods is Newton's method, Newton's Raphson method, or Newton's method, you could say. Yeah, Newton and Raphson there. Okay, yeah, thank you. So then you have secant method. Yeah, but this Newton's method is highly sensitive. This guy is highly sensitive. Highly sensitive to initial guess. Yeah. See, this secant method is also somewhat, of course, highly sensitive, because secant method we can derive from Newton's method. Newton's method, we will use, first derivative, first order derivative, and Newton's method to get the answer. In secant method, what we do, we will replace this, this differentiation stuff with a difference equation. There you can go for either forward difference or backward difference or central difference schemes. There are certain schemes to convert a differential equation to a difference equation. So out of many schemes available, central difference scheme is probably a good scheme. So that error would be somewhat down when compared to other schemes available. So anyways, so that we do in secant method. In doing this is a little bit of a jargon. I mean to say, the terminology we need to get acquainted with this. But anyways, eventually things will work out. Don't worry. So it's good to start with Newton's method first. We'll try to understand what is this method, and also we will try to come across certain functions where in overlook, or because of improper choice of initial guesses, we will go all around the root, but we will never meet the root. Otherwise, we go for divergence. So we will try to appreciate this method, that for most of the functions, he converges fast. That's it. But the only problem is you have to always take initial guess close to the true root. That's what you should know, the behavior of functions properly with open methods. Okay. If I don't know the behavior properly, then I really cannot understand what could be my initial guess. For example, this is my point of interest, my true solution. This could be one guess, or I can take this could be one guess. Okay, because the choice of initial guesses is highly dependent on the functional style or the functional behavior. So you should gain that experience. So based on the functional behavior, you should be able to take initial guesses. Okay, so that we will see now. Sorry. I can write down like this. Newton Raphson's. This is a sure short question in the examination. At least you'll get for 2 marks. Newton Raphson's method. Or sometimes you can treat this one as Newton's method. So you can take down one point without second thought. This method, when successful, works well and converges fast. That's it in one line. So when successful, it converges fast. That's it. Let me give you the much awaited numerical estimation formula for this, and then we will derive how do we get that form. Right. So this is iteration-based formula. So xi plus 1 is xi minus f of xi divided by f prime, means first order derivative xi, where xi is initial guess. Yeah. For example, you know what you call like this. Say, like I know my initial guess x1 is something. This will be given to you in the examination. So this will be given to you. Knowing this, in the iteration number 2, I go for second estimation. So I just get this way, f of x1 divided by slope at x1. Yeah, so once I get this x2 value for iteration number 3, I'll go for x3 is equal to x2 minus f of x2 divided by the slope at x2. Okay, so on, so forth. Yeah. Now I will see this. See, in open method, we don't bracket the root often, but there is one special case. Yeah, I'll tell you. In certain special cases, we also bracket the root even in open methods. So without much ado, let's take a function. So this guy is x and he is Mr. Of x. Yeah, so let me take my curve. And this curve is different from you. We don't think that always we're taking this monotonic function. Yeah, we are taking, monotonic increment function, but the fact is this, for example, the function is something like this, okay? So we are just focusing only this part of the function, that's it. The function is well defined over a meaningful domain, but we are choosing only a subset of domain, and within that subset of domain, we are ensuring that our function is continuous, and then we are working out, okay? So we are not focusing on this. The same thing is applied. If you can take something over here, the same thing is applied again. But what's the main problem here is that at a time you can't find more than single root. Yeah, that's the problem, okay? So you'll understand this with the help of spline interpolation. Why so and all? Not now, we'll do that later. So this is my actual solution. So this is my actual solution or exact solution or true value for that matter. Now you know what I do. This is my actual solution. So let me take, for Newton method, what we do, we take single initial guess. So single initial guess. In the examination, if they give, it's better. If not, then you must be able to take any one. Okay. So let me take one initial guess somewhere on this axis, say somewhere here x1. I will take some initial guess x1 here. Say my initial guess is x1. Let me start with this. I'm starting with this. I'm starting my algorithm with this. Okay. Now, what do you do without any second thought? You find functional value at x1. This is my functional value at x1. So what do you have? You have f of xn, I mean x1 value here. Now, what we do here is, let's draw a slope. Now, problem starts here. Let's draw a slope. And that means slope is what? Just a tangent, right? You need to draw a tangent so that it passes through this point, f of x1. And I will draw like this. The secant line. Okay, think it's a tangent. Okay, so this is a tangent. So this guy, this one is slope. Slope at where? Slope at x1. So I can take first derivative f prime x1. Okay, this red one is slope at x equal to x1. Now this red slope is intersecting x-axis at this point. All right. Now this is my second estimation. So see, this initial guess. So second estimation we can find out like this. I take the first initial guess minus I'll take this functional value at the first initial guess, and I'll take the slope at the first initial guess. Okay, and this is how we can find x2. Okay, this is cumulative. x2 is this, and at x2 again, what do you do? At x2 again, you find the functional value f of x2. Okay, and again same story. Again, draw a slope or draw a tangent passing through f of x2. Yeah. Okay. I'll use this. All right. So we have a slope, and this guy is Mr. So this is my slope. So this is my slope f prime x2. All right. Now this slope is again intersecting on x-axis at x equal to, say this is my x3. See, with the help of this single initial guess, so now we are producing x2, x3 estimations. Okay. Now again the same stuff. You take your functional value at x equal to x3, and this guy is f of x3, and again draw a slope at x3. Okay, like this. Let me make it proper. I drew a slope like this. All right. Now, for this problem, are we converging to the answer? For this problem, I will show you some other functions for which we will never reach the answer. Okay, we will diverge always. And for some other functions also we will take. Okay, though we stay close to the function, still we will diverge. Okay, such problems are really. One second. Which color I can take? I'll take white color. Okay. So this is my x4. At x4 again, I'll draw a slope, and now I'll go like this. So on. I'll draw here. Now I'll get the answer. So are you able to understand this? You can speak out. Did you understand this? You can speak out. I unplugged my mic. You can speak out. Just tell me. Yeah.
Yes, sir. Yes.
Okay. So that's it. So this is what your Newton-Raphson's method or Newton's method, and we'll try to prove this. Okay, now we will try to prove this this method with the help of Taylor series. Okay, and also you can make use of straight line equation. Okay, and you can get the answer again. One second, let me cut this. Let's follow a general procedure in estimating the root. Estimating the numerical value. I'll cut this. So let me use black. For example, I'll take first iteration. Let me take the case of first iteration. Okay. So I have the slope. My slope is f prime x1. Okay. The tangent is, this is my tangent line. And this point is what here? So this point is at x equal to x1, I have f of x1 value. Okay. So the tangent, so this is step 1. Step 2 is the tangent is at point x equal to x1, and at x1 you have your f of x1 value. This is your point. Okay. Anyone? How do you find slope now? Yes.
y2 minus y1 by x2 minus x.
Yeah, the tangent. Okay, I'll remove this is. Okay. The tangent at point x comma f of x1 is, let me write like this, is given by, yeah, anyone? I just want the tangent. That's it. F prime x1 is equal to what? Just the vertical difference divided by horizontal difference. Yes or not? Yes or not?
Yes, sir.
That's it. So what is the vertical difference here?
F of x1.
Correct. Very good. F of x1 minus
0.
very good, minus 0. Okay, because now you're coming to this horizontal axis. At the horizontal axis, f of x equal to 0 divided by
x1 minus x2.
x. Very good. X1 minus x2. So see, we are finding the slope, man. That's it, nothing else. So we are trying to find the slope over this interval. That's it, we did. So we found this slope. I mean, over this interval, you found the slope. You took this difference. F of x1 is here, and here you have f of x equal to 0. So divided by, we're just going like this from here to here. So x1 minus x2. That's it. Okay. Sorry. Yeah. So now what else you do? You find for x2. Now what do you get? This problem you find for x2. Now you will get, right, x2 equal to x1 minus f of x1 by f prime x1. Isn't it? Huh? So now you find, say this is my equation 1. Okay, solve equation 1 for x2. Okay, so just rearrange that equation. Okay, and it's x1 minus x2 multiplied by f prime x1 is f of x1. Okay, so what you have, x1 f prime x1 minus f of x1 is equal to x2 f prime x1. Okay, now what do? Divide on both sides by f prime x1. Now you can enjoy this form, x2 equal to x1 minus f of x1 by f prime x1. Are we clear so far?
Yes, sir.
Yeah. So you know what? Again, you find the slope. Okay, you find the slope again. This guy. So for that, you start your journey here. For next two, you just move one step ahead towards solution. You find the slope over this interval. Okay, so you take this difference and this interval, and that's it. You find for x3. Similarly, find for x4, find for x5, so on. So now we can generalize this with the help of this equation form. Xi plus 1 is equal to xi minus f of xi by f prime xi. Agree? So this is what the generalized iterative form, iterative formula. Did you understand this? Because see, I have here I plus 1 and I have here I. So I start with this and I will end up with this. Yes or not? Because the same thing will occur everywhere, right? Knowing x1, I can find x2. Knowing x2, I can find x3 and so on. So do you think this is a good form based on this observation?
Yes, sir. Yes, sir.
Obviously, see, tomorrow when you're going to develop some algorithms, you have to take something like this. Okay? Go this way, identify the behavior, and whatever mathematical stuff you have, you just convert that to a form like this. Okay, but you can appreciate this only after knowing Brooke-Taylor series. The same thing we will find using Brooke-Taylor series. So we will neglect the higher order terms. We take the first two terms of Brooke series. Okay, then again we'll come to the same answer. So we'll close now. As I told you, I'll never take any time of 5:50. Do you have any questions here?
No, sir.
Everyone, no questions? I think few are responding that they have no questions. Others, do you have any questions?
No, sir.
Okay, fine. Thank you.